Let's consider the undamped oscillator undergoing free vibration first. As we saw in the previous chart, the equation of motion for the undamped oscillator undergoing free vibration is mx double dot plus kx equals 0. Note that the time dependence of the displacement variable x has been eliminated for convenience. So we assume a solution of the form x of t is equal to a sine of omega t plus phi, where a is an amplitude of the vibration, sine, of course, is the harmonic sine function, omega is the frequency of the vibration, and phi is the phase angle of the response. Assuming a solution of the form x of t is equal to a sine omega t plus phi, we can use this solution to solve the differential equation by first taking the necessary derivatives. X dot of t is equal to omega a cosine omega t plus phi, and the second derivative with respect to time is equal to minus omega squared a sine omega t plus phi. If you take these two solutions and substitute them into the equation of motion, it yields the equation shown at the top of this chart, minus m omega squared a sine omega t plus phi plus ka sine omega t plus phi equals 0. Now you can rearrange this equation by noting that the a sine omega t plus phi is common, and you can rearrange it to yield minus m omega squared plus k times the quantity a sine omega t plus phi equals 0. Now the key part of this equation is that this equation, to be the solution of the original differential equation, must be valid for all time t. And we note that the harmonic function sine of omega t plus phi, of course, that oscillates between an amplitude of minus a and plus a over time. And so the only way in which this equation can be valid at all times is for the expression within the square brackets to be equal to 0. Solving the equation in the brackets yields omega squared has to be equal to k over m, or rewriting with the square root on the right hand side, omega has to be equal to the square root of k over m. This is one of the three coefficients that are unknown in our assumed solution. And as you well know, this expression on the right is called the undamped natural frequency and represents the frequency of oscillation of the system as a function of its two physical parameters, the stiffness and the mass. Now that we have the natural frequency of the response, we can go back and substitute it into the assumed solution, but then we realize that there's two additional variables that we need to solve for to get the complete solution for the vibrational response. We still need to know the amplitude A and the phase angle phi. Well, we're going to determine those from the assumed initial displacement and the initial velocity of the response, which we'll call x0 and v0 respectively. If we take our expressions for the displacement and the velocity and substitute t equals 0 into them, they can be related directly to the initial displacement and initial velocity x0 and v0 as shown at the first two equations on this chart. Now, these equations, we have two equations and two unknowns. Remember, we know what omega is. That's the square root of k over m. So in these two equations, x0, v0, and omega are assumed to be known quantities. We want to solve for a and the phase angle phi. So there's a few different ways to solve for these, but one of the more elegant ways to solve for phi and a are to first realize that these are trigonometric relationships, and if we rewrite the top expression as sine phi equals x0 over a, and the bottom relationship as cosine phi equals v0 over omega a, we can look at these geometrically and realize that there's actually a fairly straightforward way to solve for both the amplitude a and the phase angle phi. So let's take these two expressions and let's graphically represent them in terms of a right triangle that has one of its acute angles as phi. If we do that, we result in this expression where we write a right triangle with an angle phi. We note that the sine of phi is equal to x0 over a, and the cosine of phi is equal to v0 over omega, also over a. And so what we can realize from this graphical representation is that the amplitude a is simply the hypotenuse of this right triangle. So we're trying to solve for a and phi, and if we look at this expression, we realize that the tangent of phi is simply the initial displacement divided by v0 over omega. So the tangent of phi can be written in terms of the three quantities that we know. Then we can also see that the hypotenuse a can simply be written as the square root of the sum of the squares of the two sides. So if we do that, from this geometric representation of the solution, we can solve for both the amplitude and the phase angle in terms of the initial conditions and the natural frequency. The result is that the tangent of phi is equal to omega x0 over v0, and a is the square root of the sum of the squares, and you can see that written down in the bottom. And so this result gives us the last two parameters that we need for the complete response of the undamped oscillator undergoing free vibration. Now at this point, take a second. It's always good to take a second when you get to this part of the solution and do a little sanity checks. One sanity check is you'll note that if we look at the top expression for tangent of phi, we note that the numerator and denominator of the right-hand side both have the same units. Omega x naught has units of displacement over seconds, as well as v naught has units of displacement over seconds. And so it's fair to take the ratio of those. The ratio of those is going to be non-dimensional, which makes sense because we're trying to find the inverse tangent to get the angle phi. If you look at the bottom expression for A has units of displacement. In SI units, that would be meters, for example. And if we look at inside the bracket, we notice that x naught squared has units of displacement squared. V naught squared over omega squared also has units of displacement squared. So again, the sanity check tells us that at least we haven't messed up any of the units, and adding x naught squared to v naught squared over omega squared is appropriate. Of course, if we take that and take the square root, we get the units of displacement, which makes sense given that A should have units of displacement. So now we arrive at the solution for an undamped oscillator undergoing free vibration. And as we showed, the response is a harmonic function which has an amplitude of A and a phase angle of phi, and the frequency of harmonic oscillation is given by the parameter omega. As we found through our analysis procedure, the natural frequency omega is related to the two parameters, stiffness and mass, through the expression at the bottom of the chart. The initial conditions then determine the remaining two parameters, the amplitude of vibration A and the phase angle of the response phi, using the two solutions at the bottom. Let's plot a representative free response of an undamped oscillator to illustrate the important features of the response. A representative result is shown for the values of A and phi shown on the chart. As expected, the free response is a harmonic function whose frequency of oscillation is equal to the natural frequency of the system. The period of the response is related to the natural frequency and can be found by taking the difference in time between any successive peaks. The amplitude of the response is equal to A, and the initial displacement and velocity are both a function of A and the phase angle phi. Since this is a solution of an undamped system, the amplitude of the response will be constant over time, as shown by the red dashed lines at plus minus A.